Hello viewers, welcome to my channel Shraddha's Physics. This video is based on statistical mechanics as per the CBCS syllabus. Today our topic is statistical physics. So kinetic theory of gases is based on two basic postulates. So one is matter is made up of identical molecules and the thermal energy it can be identified with molecular motion. So these are the two basic postulates of kinetic theory of gases. And in the thermodynamics, what is the difference between the thermodynamics and your statistical physics? So in thermodynamics, it aims at studying a macroscopic system in equilibrium from a macroscopic phenomenological basis without considering the microscopic constituent of the system. It means that in thermodynamical case, we have not considered the microscopic constituent, only we have considered the macroscopical phenomena to study the macroscopic system. But in statistical case, it aims at studying the macroscopic parameters of a system in equilibrium from a knowledge of the microscopic properties of the constituent particle. It means in statistical case, we have to consider the microscopic properties so that we can the macroscopic parameters of that system. But the condition is that here also the system is in equilibrium and here also the system must be in equilibrium. In statistical case, from the microscopical properties, we have to derive the macroscopic parameter. But in case of thermodynamics, we have not considered any microscopic concept. Okay. The next is the statistical mechanics. It cannot determine the life history of any particular particle, but we can calculate the most probable behavior. Okay. The statistical mechanics, it cannot determine the life history of any particular particle, but only what it determines the most probable behavior. The step by step we will discuss it. So the statistical physics is based on the two types. One is classical statistics and another is quantum statistics. Classical statistics is also known as Maxwell-Boltzmann statistics, and quantum statistics is also known as Fermi-Dirac statistics. In classical statistics, it employs the classical result of Maxwell's law of distribution of molecular velocities and Boltzmann theorem relating entropy and probability. So classical statistics is also known as Maxwell-Boltzmann statistics. On the other hand, the quantum statistics, it was developed by Bose-Einstein, Fermi and Dirac scientists. So the essential difference between these two Bose-Einstein and Fermi-Dirac statistics is due to the consideration of particle having different spins. Bose-Einstein statistics, it deals with the case of indistinguishable identical particles having zero or integral spin, while Fermi-Dirac statistics is used in case of indistinguishable identical particles having half integral spin. So classical statistics is only a limiting case of quantum statistics. So in the next chapters, we will see what is the more details in classical statistics and quantum statistics. So we will see what is the principles of equal a priori probability. In statistical physics, equal a priori probability principle, it plays an important role. So it is a postulate and it agrees with the experimental result. So for an isolated system in thermal equilibrium, all the microstates accessible to the system, it occurs with equal probability. So it means that the system must be isolated and it is kept in thermal equilibrium so that the accessible microstates are equal probable. So I will give an example. So first of all, what is thermal equilibrium and what are accessible microstate? Okay. So otherwise it can be said that all the microstates corresponding to a given macrostate occur with equal probability. So what is thermal equilibrium? So a system is said to be in thermal equilibrium if the state coordinates, that is the length, volume, pressure and temperature etc. of a system are constant with respect to the time. So when there will be no change, so at that state we can say that the whole system is in thermal equilibrium. It means that its volume, pressure, temperature and any other coordinate, it is the state coordinate especially, they are not changing with respect to the time. In that case we will say the system is in thermal equilibrium. So what are accessible microstates? So for a given constant means the restriction, for a given constant of the system, the microstate that is consistent is called accessible microstate. So for example, suppose we toss a coin, so in that case it is so we can see that there will be either head up or tail up. Okay, there will be two possibility, either head or tail. So either will head up or the tail up. Similarly, if a 6-faced cubical dice is thrown, it is sure that the dice will fall with one of its face upward. In the same way, if we have an open box, that is, suppose it has the two compartment. One is X and another is Y. Suppose. So here the open box is divided into two equal sized compartments X and Y, and a small particle is thrown from a large distance in such a way that it must fall in either of the two compartments. So then the probability of the particle to fall in the compartment marked S is equal to the probability that it may fall into the compartment marked Y. So again, there is an equal probability. So we can say that, so there will be an equal chances of the particle to fall in these two compartments, either in X or in Y. So this is called the priority of, or we can say that this is called equal a priori probability. Every compartment will give an equal priority. Okay, every compartment will give an equal priority. So the next we will see what are the macrostate and what are the microstate. Suppose so let us consider the two coins. Suppose first two coins, one is made up of silver and another is copper. So in that case we can say that if I will toss one copper and another is silver, the two coins, so it might be the possibility the both will come as head. It has either head or tail coin. So if head is in copper, then tail will be in silver. If tail is in copper, head will be in silver, and both are tails. These are the four possibilities if the two coins are tossed. So in the first case, we can say that we can see this both head. If the two coins is made up of copper or the two coins is of silver, then in that case also the both are heads. So this is the one case. So in the next case, if we cannot distinguish between this copper and silver in the second and third case, if the both are made up of copper or the both are made up of silver, in that case if the head or tail coins in either of the coin, then we can say that one is head, other is tail. So which one is coin we cannot distinguish. So in that case we can say that this is one of the possible state. Again, if the both are tails, whether we can distinguish or not distinguish, so in that case also one state is possible. So this 1 plus 1 plus 1, so these three are known as the macrostate. These are called the macrostate. And when we can distinguish between the two coins, these states that are come, that is 1, 2, 3 and 4, all these states are known as the microstates. I think this is clear. So let us take the case of 3 coins. So when the 3 coins are tossed, so then the outcomes are the like micro. In the first case, head, head, head. Here the cases are when you can distinguish between the particles or distinguish between the coins, copper, silver, brass, like this. So 3 are head, 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 tail, head, tail, head, tail, both are heads, head, both are tail, 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 head, tail, head, tail, and tail, all are tail. So in this case you can see that if you cannot distinguish between the particles, so in that case we can say that all the 3 are head. So this is called one state. In these 3 cases you can see that any of the 2 coins comes head. So there is 2 head. This is the one state. And in the next case, here you can see that here comes one head. Here comes only one head. So you can say that this is one state. Here I am telling that when you cannot distinguish between the which type of coin you are considering, here this is for that case. In this particular case, there is no head, or you can say that one state. I am not telling that you have to consider only the heads. You can say here that the like oppositely, you can say that no tail. So this is no tail. This is one tail case. This is double tail case. Here 3 tail. Okay, in that case you can say that here the one state, and when there comes the two head, in that case this is also one state. So these are the four possible macrostates are possible here. And what are the microstate? All the individual state, that is 1 2 3 4, these are the 8 cases. These 8 cases are called the microstate. So I think this is clear. Now we can distinguish between what are the macrostate and what are the microstates. Let us take another example. Let A, B, C be the three distinguishable particles. Means you can distinguish, and we have to keep these three in two equal size compartments. Equal size compartment. So we can place these in different ways. Like suppose this is compartment X and this is compartment Y. So the no particle in the first compartment. All the three are in the Y compartment, A, B, C. The next, A here, B, C here, B, C, A, C. Then next A, B. Similarly, B, C, A, C, A, B, A, B, C. And all the three are in the X compartment and no one is in Y compartment. So here, these are all the possible microstate. Beside this, nothing is possible. So in the first case, you can see that there will be no particle in the X compartment, and there are the three particles in the Y compartment. So if we cannot distinguish between A, B, C, or we can consider the three are A. So in that case we can say that the three particles are here. So the first possibility is 0, 3. So in the second, third, fourth case you can see that I am here considering when you cannot distinguish between the particles. So here A, and here also A and A. So in that case here also A, these are A. So here comes one compartment containing one particle, and in the second compartment, that is Y, it contains, there are two particles. So in that case these three can be treated as one. These three state, it can be considered as one containing one particle and the other compartment contains two particles. So this is one state. And similarly these three, there are two particles in the compartment X and one particle in the compartment X. These three are belongs to one state, that is these are your two, this is your one. All are same type of particles, so you cannot distinguish. And in the last case, all the three particles in the first compartment and there will be no particles in the second compartment. So here the 3, 0. So all these are microstate, but this 1, this 3 is 1 and this 3 is 1 and this one is 1. So 1, 2, 3, 4, these are called the macrostate. So when you cannot distinguish between the particle, then this is called macrostate, and when you can distinguish between the particles, at that time we are calculating the microstate. So these are the examples based on macrostate and microstate. So you can see the more examples. So the macrostates are here. These are the macrostate. So this is the simple trick. You can calculate the total number of microstate, that is n plus 1, that is the number of particles. If there are 3 particles, here the case, if there are 3 particles, the total number of microstate is 4. And when we are considering the total number of microstate, it is 2 raised power n, that is 2 raised power 3, that is 8. Here also you can say that 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 microstate and there are 4 macrostate. This is clear. Now we will see what are the classical prescription. So on the basis of classical concept, so the macrostate refers to the state of the system as a whole, like pressure, volume, temperature, etc. of a system. These are the macroscopic behavior. And the microstate, it refers to the state of the system by specifying its position and momentum coordinate of all the particles in the in the system. So here comes the phase space. We will derive it later. So the next is, it is difficult to describe the microstate of a system practically because of the large number of particles involved. Next is, for a given macrostate, a large number of microstates may be possible. So the number of microstate, it corresponds to a macrostate, is thermodynamical probability. So the next comes the constraints on a system. Constant means the restriction. So what are the constraints? A set of conditions or restrictions that must be obeyed by a system are known as the constraints. So like sum of Ni equal to n, that is the total number of particles in a system, are constant. Sum over Ei Ni, that is total energy of the system E, that is constant, where Ni is the number of particles or molecules in the ith cell. I will derive it later. And Ei is the energy of each particle or molecule in a particular cell, that is the ith cell. What is the accessible state? The accessible states are the state consistent with the given constraints of the system. So what is accessible macrostate? The macrostates which are allowed under a constraint are called accessible macrostate. The specification of the total number of particles in each energy level of the system, it defines the macrostate of the system. And for indistinguishable particle, a specification of the total number of particles in each energy state, it defines the microstate. For example, there are two particles in each energy state in the energy state E3, suppose. But the condition is that one particle must be in any two cells. So the first case is one cell, two cell contains one particle. So this is the first case. 1 3, second, 1 4th, third, and 2 3. So these are the possible states which are possible. So the degeneracy is 4. Suppose in the next case it is given that the second energy state is filled up with 3 particles and there are 3 cells, and the condition is that one cell contains 1 particle and the other contains the 2 particle. So in that case, the first case is 1 contain 2, the second one is 1. So this is the first case. In the second case, we can say that there are 2 particles and this is 1 particle, the second case, and the third is here is 1, here is 2 particles. So these are the 3 possible conditions. So the degeneracy is 3. Similarly, for the third case, if the first energy state contains the 4 particles, so since there is only one cell here, so we can say that the 4 particles will contain in this cell only. So there is no other cases, so the degeneracy is 1. So here the accessible macrostate, the macrostates which are allowed under a constraint are called the accessible macrostate. So in distributing the 3 particles in 2 cells under the constraint that no cell will remain empty, the only accessible microstates are 2 1. Okay, distributing 3 particles, there are 3 particles, so there are 2 cells, so 2 cells 3 particles. So the condition is one will contain 2 particles, other is 1, and one contains 1 particle, other will contain 2. These are the 2 possible cases. So this is 2 1 and 1 2 cases. These are the accessible macrostate. What are inaccessible? The macrostates which are not allowed under a constraint are called inaccessible microstates. It means that in these cases, 3 particle, 2 cell, there are 2 cells, 2 cell, 3 particles, but the constant here is no cell remain empty. If no cell remain empty is an accessible macrostate. So no cell remain empty means 1 contain 1, here contains 2, or it contains 2 particles, here comes 1 particle. So these are the accessible, but inaccessible macrostate says that it will not follow the constraint. That it means that one contains 0 particle, no particle, other contains the total number of particles here also, and also one contains 3 particle, other compartment contains no particle. So these 2 cases are called the inaccessible macrostate. This macrostate is not accessible. By following the certain rules, we can say that by following the certain rules, so this condition is satisfied for the accessible macrostate when the constant equation follows, it called the accessible macrostate. Otherwise, we can say that when the constant equation doesn't follow, it is called inaccessible macrostates. The next comes most probable state, or this is called equilibrium state. So the most probable state of a system is that macrostate which has the maximum probability of occurrence. This is the maximum probability of occurrence. Suppose for n particle distribution in 2 cells, there are 2 cells, n particle is to be distributed. So the probability of occurrence in the most probable state is P max will be n c n by 2. This is the combination n c n by 2 divided by 2 power n. So in static system, the thermodynamical probability of the macrostate n1, n2 is W will be equal to W, or it is denoted by omega, equal to n factorial divided by n1 factorial into n2 factorial, that is equal to n factorial divided by n1 factorial, or this in place of n2 factorial we can write n minus n1 factorial. So that will be equal to nc(n1), or that is equal to nc(n2). This is the C means the combination. So this is the case of in statistics system. We will go in detail in the further chapter. So in dynamic system, for a large number of molecules in the two compartment, when undergoes collision, the number of molecules in the compartment go on changing, and the system moves from one macrostate to another in very large number of times per second. Some macrostates are more probable than other depending on the frequency of the microstate. Frequency means the number of times of occurring. When the number of particles in a dynamic system is very large, the system exists practically all the time in the most probable macrostate, because even for small deviation from the most probable macrostate, the microstate fall extremely rapidly. So this is called equilibrium state of the system. So otherwise, in simple sentence you can say that the system where the particle lives for the maximum time, or it stays for maximum time, it is called the equilibrium state of the system. So this is all for today. In the next class we will see ensemble of a system. What are ensembles and